Good morning. I know I'm only standing between you and your next coffee break, so I'll try and stick to the time limit. So when I was preparing this presentation, and I found out it was MIT, I thought, let's focus on the data. And then I was thinking, what's a good analogy between the effect that noise has on MEMS structures? So we've all flown here on the airplane, we're on the taxi, we go into the runway, and they come out with the announcement, please put your laptops and your iPads away. And then you have a beautiful mom and dad of a 5-year-old who's playing a game, and they take the iPad away. And that beautiful child turns into a screaming banshee and lets out an acoustic noise that everybody in the plane just goes, it's like, you're just stiff. That can have the same effect on MEMS. So when noise is very prevalent during the test process, you can have that type of effect. Another effect, you're driving your new Chevy at 80 miles per hour in a 55 miles per hour zone, and you hear that familiar wailing sound. Clearer? See, noise, that's the problem. It was all part of the show, don't worry. So you're doing 80 and 55, you hear that familiar wailing sound, but this time it's accompanied by little blue and red lights. And it's like, I'm so busted. And so, which button is it to go forward? Ah. So traditionally, we are handler companies. And handler companies, when we first got into MEMS, it was like, how do we design the stimulus to suit the handler? And using that approach is great for legacy products. But now, as Meta just mentioned earlier, the requirements for sensors, accelerometers, gyroscopes, microphones, the specifications are getting so tight. The silicon is getting smaller and smaller. So noise has a huge impact on the effective test. So at Cohu, we were thinking, well, we look into the future now where we're becoming more and more MEMS sensors in everyday lives. What's the best approach? So we kind of flipped the coin, so to speak. And we said, let's focus on the device and the test. Let's develop the stimulus first, and then figure out how we handle the devices to get them into the test environment. And so we realized that we need to decouple the actual stimulus unit from any handling mechanism. By doing that, you minimize any interferences, but you also have a design that maximizes the DUT freedom. And by doing this, that gives you the most flexibility to ensure that any noise, whether it's mechanical noise, electrical noise, or general noise, has the least effect on the sensor itself. So let's focus on the DUT. So one of the first things we came out with, we call it G-Sense. G stands for gyroscope. It's very high parallelism, up to 250 in parallel, depending on the package size. As you can see from the little animation there, we have the full dynamic axis. And we eliminate the maximum noise and vibration in the system itself. And how do we do that? So we said to the designers, let's focus on the rotation axis first, because typically that generates noise when you actually rotate the device, or in this case, there's several devices. And so we focused on the noise and the vibration that could reach the DUT based on the design. This presentation is more focused on the results and the data as opposed to the system itself. And as you can see here, we are using a fiber optic measurement system on the rotational axis itself. This is not mounted onto the system yet. We just wanted to measure the noise. And as you can see in the chart, the very key factors here is the wow and flutter for gyroscopes. They really affect the calibration of it when it's running. And the customer specifications we see at the moment, they need less than 0.5%. When we measured this using this fiber optic measurement, the largest measurement we found, as you can see in the screen here, is 0.095%. And that's including the measurement noise itself. That's why we have a nice green smiley face there. So we know now that the rotational axis doesn't generate noise. But now you've got to realize this system is going to run in a production flow environment. So you're going to get people walking past, you're going to have people shouting, you're going to have machines running next to the machines. So the next factor we've focused on for the noise is the decoupling from vibration. And so we set up, as you can see in the photograph, we have a sensor on the rotation axis itself, and we also put one on the floor right next to it. And we had an apprentice driving the truck, the forklift truck, back and forth past the machine and screaming and shouting and playing music. And as you can see on the red line axis is the actual effect on the floor. And on the blue line, which you can hardly see, but the blue line axis is hardly impacted at all. So we actually can not only isolate the electrical noise, we now can isolate mechanical noise that you get in a production environment, which is very key when it comes to the calibration of the next level gyroscopes that we see in the market. In addition to this, we also focused on microphones. As we know, microphones, before COVID, there was supposed to be a big ramp in high SNR microphones for voice activation, voice security. We are seeing it in more and more of the devices that we use today. Cars, I just got a new one and I can talk to it. It's weird, car answers you back, but it can pick me up when I'm driving as well. And so we focused on the two aspects of microphones, especially for the high SNR levels. And you can see in the picture here on the top, we put a grass microphone on the outside to measure the external noise. And then inside our sound isolation chamber, we put another low-end grass microphone to measure the internal noise when we played some pink noise. And as you can see, even at an 85 dB level of pink noise, internally, we are measuring around 13 dB, which is really, really a very accurate sound isolation from external noise. Now, the reason we were focusing on this is because usually for testing microphones in a production environment, some people have to build anechoic rooms, which is very costly and not very good in an OSAT when it takes up space. In addition to this, again, people were saying, well, fine, you don't need an anechoic room, you can isolate it from sound noise, but what about vibrations? People walking past, trolleys going past. So he said the best way to test this, because Cohu has its own turret systems, let's bring a turret system, put it next to the isolation chamber, and run full production mode on this turret itself. The turret generated a noise of around 87 dB, but for those who've ever been in a production flow environment with turrets, they're really noisy and they cause a lot of vibration. And we were able to isolate the vibration from inside the sound chamber as well, also down to 13 dB. So when we had a customer coming up to us and saying, well, fine, Nigel, you can isolate all this. What is the effect on a DUT? I will give you a DUT of 74 dB. Can you test it in a normal production environment without anechoic rooms, with normal people going past and vibrations, and what type of data can you get from it? So I said, before we do that, let's see if we are repeatable. And what we did, we took the customer's device and put it in several locations in the sound isolation chamber, and we tested the device 200 times repeatable. In the bottom chart, the histogram is actually showing you the deviation across the reference microphone. Being a grass reference microphone is very, very accurate. But even the device under test, the customer's device, on the top chart, you can see the deviation. The spread is very, very small. Customer always said they can't achieve this themselves, even in their lab, and this is on a production version. And so we did the test, and they asked us to do it at 2 levels. First, just do it at ambient noise. In your assembly area, it's roughly 48, 49 dB. There's a spike. That was somebody just shouting, Nigel, your machine is running. And then again, we did the pink noise at 80 dB. The 2 bottom lines around the 13 dB mark is actually the internal grass reference microphone, showing exactly what the sound isolation is measuring. And the 2 measurements, it's actually red and blue, but it actually looks like one line. At 20 dB is the customer. So that's a 74 dB SNR device really measuring down to 20 dB. So extremely accurate. This system is available, and I have a little video which is just going to run in the background as I'm talking through here because it's a very fast system. This part of it we call Sense Plus. This is the base system model. This is completely mechanically isolated from the stimulus, and you can move different stimulus in. You can have a gyroscope test, pressure test, microphone test. It really depends on the stimulus. We're not using a standard handling system. If you remember in the beginning, I said we focus on the DUT and then figure out how to get the devices there. So we decided let's use a robotic arm. And let's use a carrier where all the devices are put inside up to 250. And therefore, the robot arm can then pick it up from the handling system and transfer it to the decoupled stimulus system. The advantage of this, there's no effect from noise, whether it's mechanical noise, electrical noise, or general noise. After this is for the gyroscope test, then goes to the gyroscope. This is 192 devices in parallel for a customer. We have a stable angular velocity. After it's finished, it's exchanged from tested parts to non-tested parts. It then goes back to the Sense Plus model, where we will do full 6S inspection. So you're having the same system doing the inspection of it and then going to tape and reel. So instead of waiting to go to another department to have finishing, you can actually do everything on one system with the highest specifications available in the market at the moment. Here you can see the 6S inspection, and that is the Sense Plus system. And I've got 3 minutes left, so you got an extra 3 minutes for coffee. Thank you.